Right, welcome back. This is one of the chapters that a lot of students seem to dread is the chemistry, but I really want you to think about it as a chapter that gives you the insight that you need for the rest of the course to think about how things work and interact and that sort of thing. So uh, hold your judgment until we're through with this section, and we'll see what you think about that. So we're gonna talk about the atomic structure of atoms and what they're composed of, the types of relationships these atoms have, and there's a lot of very interesting things that the scientists and physicists have come up with, using linear accelerators and all sorts of things. But that goes beyond the scope of this particular course. But just know that there's a lot of very interesting things you can find out there. And then we'll talk about the interactions with water and how important that is for all of life. So I guess we just start with the obvious, that everything is made of atoms. And I'll tell you up front that we don't know the details of atomic structure as far as why it works the way it does. We can measure it, we can see it, we can hypothesize, we can predict, we can write equations, but we're still pretty much in the same boat as understanding what gravity is and those sorts of things. So I'll make that right up front. It's so if you're thinking about maybe going into a particular science, no, not everything has been discovered, and there's plenty of opportunities. Back in the 1800s, the latter part of 1800s, they were going to close the U.S. Patent Office because they decided, or someone decided, that everything had been discovered, and there was no need to keep the Patent Office open because, well, we just won't patent any new things. And that's the mindset that I don't want you to have. I want you to have that it's a wonderment, and there's so many opportunities out there for new discoveries. And so lest I digress, let's move on. The element is a substance that cannot be broken down chemically into any other substance. So an atom is a bit of matter that cannot be subdivided any further. So when we talk about these two things, you have to think about, in the early days, Sir Isaac Newton and other famous scientists of the time trying to morph one substance into another, and unless you have a linear accelerator, these alchemists could not turn lead into gold. But if you had a $3 billion linear accelerator, you could get maybe a few atoms of gold from lead. So technically the concept was there, but the way those early scientists went about it was an impossibility. Anyhow, so these are true unless some extraordinary circumstances come into play, is all I'm saying. So atomic structure. So you probably have heard these sorts of things, and it's important that we go over it just one more time. The atomic structure, the basic structure for elements other than hydrogen, is that we have protons, neutrons, and electrons. Now, in a hydrogen atom, we don't have neutrons. The way I'd like you to think of neutrons is sort of the in-between to keep the two opposites, the proton and electron, from hurting each other or getting into trouble. It's sort of like the boxing ring. The coach or the moderator for that is making sure the two sides are playing nice. And so the neutrons are sort of the go-between, the protons and electrons. So if you notice, for every proton that has a positive charge, there's an electron that has a negative charge. And that's sort of the association I wanted you to think about. And because of their opposites, they attract. You know that. Things that negative charge will attract a positive and vice versa. And it's sort of what makes everything kind of work. Now, that attraction, we don't obviously it's easy to think of it as a positive negative, but if you get into the real molecular aspect of that, it's quite interesting. Why is that? And if you look at the arrangement, now I don't want to mislead you with this graphic. If you look, we have the electrons and the protons, and these are sort of orbiting. Well, the new thinking of what, 30 years ago, 40 years ago, this is a cloud, and the probability of where these charges are could be anywhere. They don't technically orbit like that. It's probability, but it's okay. That goes beyond the scope here. So in atoms, everything around us, living or not, that can be reduced to atoms. All atoms, whether of the element gold or some other element such as oxygen or aluminum or calcium, have the basic structure. At the center is the nucleus, usually made up of two types of particles called protons and neutrons. So those two are in that very close association, and they're particles that have a positive charge. Neutrons have no electrical charge except they're associated. Now, I tell you this, and I literally cannot tell you what a neutron or a proton is actually composed of. It's just we can measure, and we know that these are particles, and it's mass. Protons and neutrons have approximately the same mass. That's about all I can tell you, and it's from what we know. So if we bring it down to the electron shells, and again, this kind of brings the notion that we're talking about orbits, but they're shells of probability where this electron could be anywhere in that cloud or that first shell. And then the second is the second shell is, if you notice this, there seems to be a certain number here. Is 1, 2, 3, 4, 5, 6, 7, 8. Seems to be 8 electrons in that shell, and it is true. And I'm going to talk about something called the octet rule, and it really help you in terms of understanding what's going on. But atom stability, this is a key point. Unstable, like hydrogen, needs to have one more to be fully stable, like helium. And so the first grade or the elementary school kindergarten report card, helium did not play well with others because it doesn't need anything else, and they refer to these types of atoms that are fully filled with it satisfying that outer shell. These are inert. In other words, they don't interact, and they have helium has some interesting properties and various things. Hydrogen, of course, wants to bind or fill that seat if it can. It's short one of the electrons. That's what makes hydrogen, and it's more interactive. So the hydrogen atom will bind with something else, and it will share, or however, to try to become more stable, sort of wanting to do that. So that's a driving force, and we're going to talk more about that. Nitrogen and neon atoms, you can see the same sort of relationship. The nitrogen needs additional electrons because we have seats available, and they call this the valence, the outer shell. And to fill, or to get the full octet rule satisfied, you need to have all 8 of the electrons, like neon. Now neon is inert just like helium is inert, and this doesn't play well with others, and that's where we're on that for. And the electron shells are so important in determining how they interact based on the vacancies amongst each other. So that's kind of the relationship we're going to be talking about. And so I'm going to try to limit our discussions to things that are just relevant to biologists, and those will be the elements that are associated with the human body and living things. And pretty much the top 10 you can see listed here: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chloride, and magnesium. And it's interesting, all of these obviously can interact because it needs some level of fulfillment in the octet rule. the fill-in is pretty obvious is once we get into looking at the periodic table, which we're going to get into here in a little bit. If you notice, there's also trace elements down here that aren't used as much, but they're still very important, and there's some really interesting arguments and discussions about all of these things as far as humans. But boron, chromium, copper, cobalt, fluorine, iodine, manganese, molybdenum, selenium, silicon, tin, vanadium, and zinc, all are still important for various things. And we're going to talk about proteins made up of amino acids and all these other chemical compositions based on oxygen, carbon, and hydrogen. But some of these proteins, when we talk about these, don't worry about it right now, need these other sort of enhancements to have some chemical and electrical characteristics that it could not achieve otherwise. So that's why we have the interactions of all these things. But we're going to focus on the top 10 for right now, and hopefully help. All the known elements can be arranged in a scheme called a periodic table. And there's a lot of interesting history. I'm not going to go into that right at this point. But a gentleman, while he was sleeping, supposedly, came up with this notion, a concept of being able to arrange these elements in a certain pattern, which we call the periodic table. So there's a lot of very interesting concepts about consciousness and sleep and all these sorts of things, and we're going to kind of look into this a little bit later on as we go through the course. And I'd love to get your feedback on various things and how these affect experiments and all sorts of interesting things. So I guess what I'm saying is that I like to sort of push the outer limits and get your mind to expand a little bit, and not just regurgitate these little things that we talk about. Only that. Keep it open for wonderment there a little bit. So everything you see around you is made up of some combination of the 90 or so naturally occurring elements, and some of these are man-made. We'll talk about that. And of all the elements found on Earth, about 25 are in your body, roughly. I gave you the chart. The top 10, the most common, make up the 99%. So we have that. In on Blackboard, I have placed in course resources your very own periodic table, and it's in the listing there. You can just click. It's a PDF. It looks like this, and it shows in colors at the top the element categories, and this is an arrangement of the periodic table. Now, one is missing here, and I don't know why that is, but it's the hydrogen should be here, but there's helium, and then it goes on down, and I'll have to dig in to find out. It may be some graphic issue here, I'm not sure, but anyhow, the hydrogen's there, and then you go through and there's some others not listed for whatever reason, but that's okay. It's just a glitch. You can go and look at it on the course resource area, and it'll be complete. It must be something with PowerPoint. But periodic table, so we have columns and rows, and there is some really interesting aspects or relationships based on that. Now I'm going to use a subset of this periodic table and kind of shrink it so we don't have as much data staring us in the face. I modified it. So here's a modified periodic table, and all I did was to take the top part and kind of shrink it together, so we just kind of move out all of this area in here so that they still follow sort of the same pattern. And what I wanted to do with this is to show you the relationships, and you start to see these. So the first orbit, as I've mentioned prior, is to have two. So if you look at the inert, helium has 2 electrons, the maximum number in the first orbit, and of course it's not really orbiting around it. They can be moving around at any area of probability, but there's 2 of them. That's the maximum. This is an inert compound, helium, but hydrogen needs 1 more. So if you look at the relationship, we're going from left to right, and the fully satisfied ones are on the right side, and as we get and approach the right side, we have different levels of completeness of the octet rule, which is the number 8. Now, what this refers to, if you look at the outer shell, so we satisfied the inner shell. So the very first row, we already now know from the periodic table, that refers to the first shell, the second shell, third shell, and so on. And so in the second shell, we have 1, 2, 3, 4, 5, 6, 7, 8. That satisfies the octet rule of 8. And neon is fully satisfied, and that's all the way over on the right side. The least satisfied is lithium, and you can see that is all the way to the left. So as we go across, you can see we're adding one more outer electron as we go, which adds one more proton. The first shell is satisfied, so we don't even worry about that. And so that's why we call it the octet rule at this point, is we're satisfying all 8 with neon. If you look at carbon, it's halfway there. So 6, technically we have 6 electrons, 1, 2, 3, 4, 5, 6. But don't let that confuse you. The outer shell, what they refer to as the valence number, has a maximum of 8. And that's the key point, is we're going to only worry about the elements that up to the third shell here, and each shell since the first one, second and third, the maximum number is 8, and that's the octet rule. So this carbon has 4 in the outer, 5, 6, 7, 8. So that fully satisfies the octet rule. Yes, there's one more shell on the inside, but that number doesn't change. You can see once we get past the first row and get in the second row, now we're worried about the second shell and then third shell as we go on. So 1, 2, 3, 4, 5, 6, 7, 8 is the octet rule, but we have to add the 2 more, and that gives you the full number of 10 in terms of the number of electrons. But that is because of the first shell having the 2 filled, but it's sort of superseded, or the valence. A valence is a funny word. It's sort of like a bumper in the car. The outermost part of the car could be called a valence. The valence is the outermost shell. And what is the valence number? Well, carbon has a valence number of 4 because of the octet rule. So I like to refer to it as the octet rule, but if you do come across in the literature about a valence number, it's sort of the same thing. It's the outermost number of electrons in the shell. And I hope that makes sense to you. So let's look at the octet rule a little bit. So in this particular compound, we're looking at neon because all of the electrons seats are filled, and so we have 1, 2, 3, 4, 5, 6, 7, 8 that fills the octet rule, 9, 10, and so that we're at neon. Okay. And so that's octet rule. Let's kind of take a different rule here. Very first one, the hydrogen, which was for some reason missing on the original table there. Hydrogen, we need one more. Helium has the full satisfies the first shell, and the octet rule is satisfied with 2 in the first case, and that's helium. Now we move to the second row, and you can see and so on and so forth. We fill in that, and then the outer shell of these on the third row, if it's 1, 2, 3, 4, 5, 6, 7, 8. So if all 8 are filled, it's argon, has 18 electrons, but it has 8 in the outer valence, and that satisfies the octet rule. And then you count down the number in the outer shell of electrons, and you can see we move chlorine, sulfur, phosphorus, silicon as we go across. The sodium is the very first one with only 1, and we see sodium a lot for lots of reasons. and we're going to talk about the types of bonds and things like that in a little bit. But you have to understand the octet rule is a gauge really of how much it's going to interact, because if you're not fully satisfied, the more of a need. Now, I know that's not very technical, but it's true. So the fewer electrons in its outer shell, the more stability that it needs to acquire by whatever type of arrangement of bonds or things that it does. It's trying to achieve that stability. So we're going to talk about that next, moving on. So we have the first shell referred to the first row. We go to the second orbit or shell, it goes to the second row, and then the third, as you can see, that relationship. So now when you look at a periodic table, I hope that it's now going to make more sense to you, because that it has a rhyme and reason. It has an association to it, and this is true across the board. Now, the octet rule changes as we go down the chart a little bit. We're not worried about that for right now. It goes to instead of 8, 16, but that's okay. We're not going to worry about that. As far as we're concerned right now, I'm only worried about the elements of the human or of life, and that's where we are. So the key to the elements, there's certain, on the periodic table, certain numbers, and we have the atomic number. This is important, and I do want you to know what an atomic number is. The number of protons found in the atom's nucleus, and that's an important number. The element symbol is abbreviation of the element's name. Now, there are some exceptions, like gold. It's not GO or something like that. It's AU, because in the old days, aureum, Latin, aureum meant gold, and AU is gold. And so there's a little bit of some of the, there's only like 4 or 5 exceptions like that. But oxygen, the atomic mass is the average atomic mass of an element's isotopes weighted by their abundance. So we're going to talk about mass versus weight. Now, our weight on Earth is whatever it is. You go to the moon, and our weight is 1/6 of that. So you take your weight and divide it by 6, and that tells you roughly what you weigh on the moon. And it's a reflection of gravity effects. Where mass, we have the same mass on Earth as we do on the moon. Okay, so it's a different parameter. It's a measurement that is devoid of the effects of gravity. Let's put it that way, and I hope that helps. Your book is nice because it uses these colors throughout the consistency in the book and the reading, and it's just nice to know when we see representations of various things, that hydrogen, carbon, nitrogen, oxygen, sodium, phosphorus, and blah blah blah, and they have certain color codes, and it's only in your book. It's not anything particular. Now, if you recall, I made some reference to the area of probability. And here you go, here's the area of probability, and it's obviously denser as the closer you get in, because there's not as much room around the nucleus, and then the area of probability. So these is where, out here is where the electrons are flying around, and this is the best that I can say at this point. So if you look at the nucleus, we have the protons, and then the molecular glue, the neutrons, and then the negatively charged electrons are flying around. And typically a good measure is 1 angstrom when we're looking at atoms at the atomic level, and it's really, really small. That's at the molecular nanoscale, not quite there with an angstrom, but we're close. And nanotechnology is getting really, really close to the atomic size of things. It's amazing. So it's 100,000 femtometers, which is just the same as 1 angstrom, and with the helium atom. So you can see it's pretty interesting. It's not totally understood or delineated, although the physicists have done a lot since Einstein's time. So there is this weird situation called an isotope, and the isotopes are atoms with the same atomic number the same number of protons but different in atomic mass are isotopes. And they use carbon. The reason I bring this up is that we carbon date things. And carbon dating is a useful tool to figure out how old things are. It's controversial by some scientists measure, but the atomic number is the same number of protons, but the atomic mass is different. And over time, we see that carbon 12, carbon 13, and carbon 14, the relationships will change in terms of its concentration. If you're looking at an Egyptian mummy or something, the relationship, the concentration of each of these will change as a result of time, and that's what they use. But those are isotopes. So more or fewer neutrons, the atom's charge doesn't change. That's one of the really key number, but the atomic weight changes. Not where the atomic mass is shown as 12, 13, and 14. In fact, I've always referred to it as atomic mass. I think the book refers to it as atomic weight, which I guess if you put atomic associated with it, it's the same. But the weight is with the effects of gravity. So the atomic nucleus of any element is made up of protons which have a positive charge, neutrons which have no charge. This is just review. Each atom of each element always has the same number of protons. So the different varieties of an element called isotopes may have different number of neutrons. So the atom will always have one proton but can have 1, 2, or 3 or neutrons. So the neutron number, the amount of glue, I guess you could say, changes. So here's hydrogen, deuterium, which has got 2, and then tritium, which is 3, and you usually see a superscript 3, and then it shows you the number of electrons down at the bottom part of that. Is a kind of, and so you may have heard of water that has it's deuterium or tritium and those sorts of things. Those are isotopes, and it's just changing the number of the neutrons, and it's just important. Oxygen has also isotopes, and so we have O16 and O18 in terms of the neutron numbers, and protons and neutrons, and so it reflects into its atomic mass. That's all I was trying to get across. Radioactive atoms. Few atomic nuclei are not stable and break down spontaneously. These atoms are called radioactive. During the decomposition, they release a constant rate, a tiny high-speed particle. So we have alpha, beta, and gamma are the 3 types of energies that we are aware of. And alpha is the least one to worry about. There are some elements that give off a radioactive, let's say phosphorus or something like that. There are beta emitters like radioactive sulfur, and then gamma. Gamma is the worst. It goes right through you. It can damage DNA and all sorts of things. Betas can damage DNA as well, and so radioactive really can kill a cell pretty quickly. Now the alpha is the lowest power of the 3. So what is radiation? The nuclei of some atoms are unstable. In order to achieve stability, they emit radiation. So we call these radionuclides, and they're radioactive. Radioactivity is a nuclear process, is not a chemical process, and it's not possible to control the rate of the radioactive breakdown of these radioactive atoms. So the energy given off in the particles, and here's sort of what we worry about with the radiation symbols. And so we have 2 protons, 2 neutrons, alpha radiation, high energy electron being given off is beta, and then high energy electromagnetic photon is gamma. These are the high power ones that shoot right through you. People that do spacewalks, astronauts and the like, have a lot of gamma radiation exposure because they don't have our Earth's environment that's protecting them, and also the beta radiation. So these are decaying of these radioactives by losing these, and it's trying to become more stable as a result. According to 2010 survey of energy accidents, there's been at least 56 accidents in the United States. And I didn't know that, so I was reading up on some of them, and there a lot of it is just human error, just silly things, people falling asleep when they should be paying attention, or falling into some of the reactors, or accidentally putting two sources too close together. It's just all sorts of weird stuff. But there's been some major ones that you may have heard of. The Fukushima disaster in 2011 is the one closest to my memory. It was a horrible event after a hurricane brought in a tsunami into the coast in Japan, and it caused a huge amount of damage to the reactors, and they had fires and they had to put it out. But unfortunately, some of the reactors went critical. In other words, the reactions become spontaneous, and they call it the China syndrome, where it just burns right through the earth until it goes to the other side. But I guess if you're already near China, then they probably call it some other syndrome. I don't know. We're not going to worry about that. But anyhow, it's a terrible thing, and the radiation effects of this was huge. A lot of people did get that died as a result of this, either at the event or trying to help clean it up to manage the event. And we do see in several papers talking about the radioactivity is spewing into the ocean. It still is to this day, and certain things have floated across the ocean and have arrived at the California coast, and there are radiation detectors which had to be shut down because they were going off. It does show you that the radiation has moved around, and so unfortunately we're all in the same bathtub, and we can get the effects of these things. You just don't hear a whole lot about it, but that's okay. Other ones that were rather large that we worry about is Chernobyl. This was an accident that occurred in 1986, and the main reactor went out of control, and it's to this day is still. They've built a huge cement covering over the whole area, and they try to cap it off. But even to this day, you get close to this area, you have to speed on the highway with your windows up as you pass this to minimize any exposure. So it's still to some degree emitting radiation, and there's other stories, but I don't want to go into too much of that. It's beyond our scope. And then the 3 Mile Island disaster in the United States in 1979, a failure that happened, and it really it's marked as the worst U.S. nuclear accident. Not as severe perhaps as Chernobyl, and nowhere near Fukushima, but it's one that we have to acknowledge that it does happen. And the same class of reactor that Fukushima experienced a meltdown, we have many of those. The Sharon Harris plant here in North Carolina is of the same class as that Fukushima, is my understanding. So the 3 Mile Island, you can see where that's located, and it's pretty it's located by pretty high density areas of people where they live and that sort of thing. It's a huge concern. So much for that. So let's get back to the elements, and 25 elements of your body. The big four are the oxygen, carbon, hydrogen, and nitrogen, and we spent a little bit of time on those during the course because they're so well utilized in the human body, but not to forget all the other members as we look at this. Whoops, not the atomic structure, but the atomic structure. I don't know why I did that. That's weird. I'll fix that in slide set. But anyhow, I thought the graphic looked pretty cool, so I wanted to include that. So the summary for this is everything around us, living or not, is made from atoms, the smallest unit in which material can be divided without losing its essential properties. Atoms all have the same general structure, and they're made up of protons, neutrons in the nucleus, and electrons which circle around us. And we have all sorts of interesting things. The chemical characteristics of an atom depend on the number of electrons in its outermost shell, and atoms are most stable and least likely to bond with other atoms when the outermost electron shell is filled to capacity. So we're going to stop here and pick up on part 2, which will get into molecules and bonds, energies, and chemical reactions. But let's have what we discussed soak in a little bit and get the relationships pretty well structured in your mind. And I'll see you back in part 2, and we'll move on from there.